All right, guys, welcome back. Let's get to this activity. The problem says the speed v of a ball can be determined by the equation v is equal to the square root of 2 times k over m, where k is the kinetic energy and m is the mass of the ball. Okay? The question asks, simplify the formula if the mass of the ball is 3 kilograms. All right, a lot to unpack there. So let's first write this formula. The formula is V is equal to 2K over M, right? And this K, as the text says, is kinetic energy. You may or may not be familiar with that. It's just a unit for energy, right? And M, the text also says that it's mass. Cool. So this bottom portion here, it says the mass of the ball is 3 kilograms. So mass is equal to 3, right? So then that implies that I can just make the substitution 2K over 3, right? Is there anything else I can do with this? Some people may suggest, if they remember their root properties, and suggest 2k, the square root of 2k over the square root of 3. Why did we do that? The rule that we were using just now was the square root of a over the square root of b is equal to the entire thing, square root over ab, right? So that's what I use from here to here, right? So now we're here. Both are the same. Is there anything else we can do? So today you're going to learn about rationalizing the denominator. I don't think this is the first time you guys covered this. Maybe in your last year with Swanger, you guys did this, you might recall. Rationalize the denominator. Or for short, because that's huge, let's just refer to it as RTD. Right? So what rationalize the denominator suggests is that if I have 2k over the square root of 3, right? Rationalizing the denominator means that whatever's in the denominator, I multiply top and bottom by it. So square root of 3, square root of 3, right? And what else can I do here? I can put these two together, meaning 2k times 3 and 3 times 3, right? The rule that I used here was the rule that I used last week, which was square root of a times square root of b is equal to the square root of a times b, right? So if I had to have two radicals, I can put them together as so, right? So now I can just multiply the radicands of both radicals, and I have 2 times 3 is 6k square root of 6k, and the square root of 3 times 3, which is 9. Right? And the square root of 9, we can continue. Square root of 9 is 3. And since there's no two like terms because of the invisible 2, since there's no two like terms that'll give you 6, and there's no two like terms that'll give you k, then this is in its simplest form. So then just carry this over. And so the final answer for this, when we substitute it in the 3, the final answer for this is this. Is that piece, right? The difference between this piece and this piece is, one, well, we rationalize the denominator by multiplying top and bottom by the denominator, right? And the reason we did that was because rationalizing the denominator is a standard in mathematics. It seems like a hassle right now, but let me offer you a quick explanation before we move on as to the benefit, another benefit of rationalizing the denominator. So if why RTD? Why rationalize the denominator? Well, because think about it like this. If you have the square root of 2 times k and the square root of 3, this is a radical expression, versus, right, versus the square root of 6k over 3, right? So in this example, this one is not RTD, right? Because you have a radical on the bottom, and this one is. Yes, RTD, because there's no radical on the bottom, right? So suppose I tell you to add 1/3 to both of them, right? If you add 1/3 to both of them, in which case would it be easier to add the fractions? In the case where they share the same denominators here, I should say, or in the case where they don't share the same denominators because they're not rationalized. So I hope you see now the benefits of rationalizing the denominator, because whenever you're adding anything to a fraction, the fraction by convention is always going to be rationalized. You're never going to have square roots in the denominator, or you should never have square roots in the denominator. Cool. Moving on.